everyone, welcome back to Learn Computing with Daniel Bullen. I'm Daniel Bullen, and today we have something special lined up for all you budding computer scientists and students out there. So we're going to do a dive deep into the GCSE Computer Science Computational Thinking and Problem Solving paper for the AQA exam board, and this is the 2020 paper. So we're going to break it down and we're going to make it a breeze for you. But before we do that, if you haven't already, hit that subscribe button and ring the notification bell so you never miss out on our tech-tastic content like this. And all the links to my channel, my online course, and my other stuff I have to offer is below in the description. So please check it out. But anyway, let's get right into it. I'm not going to read the instructions because, yeah, you all know that, and the invigilator will read that for you before you start the exam. So let's get right into it. Question 1. A bitmap image is represented as a grid of pixels. So what's a pixel? State what is meant by a pixel. So a pixel is a single point of color in an image. That's all you need to say for 1 mark. Question 2. We've got to state the maximum number of different colors that can be used if a bitmap image has a color depth of 6 bits. So it'd be 64. Or you could say 2 to the power of 6. Any one of the two would be fine. All you need is either 64 or 2 to the power of 6. No working involved. Let's get to part 3. What is the minimum file size? So what is the minimum file size? An 800 pixel by 1000 pixel bitmap image that uses 20 different colors. Should give your answer in kilobytes. So this is where we need to show our working. So let's say, for example, I wanted to, to do this, it's 3 marks. So you could do something like, to get you 3 marks. So we know we've got 500. So to get that, we would need to do 800 times 1000. So 1000 is like the color depth, 800 is the file size for a pixel. So even if the color depth is it, so what will happen is we've got, so in this one, so the number of colors is 20, which is what we want. So it's 20 colors. So let's say, for example, it's going to be 5 colors per pixel. So if it's 20 colors, it's going to be 5 colors per pixel. There's 20 divided by 4 is 5 because a pixel's a square. So we've got that bit. So the total pixels width is going to be 800 times 1000, which is going to give you 800,000 pixels altogether. So what we'll need to do is we will need to do 800,000 times 5 bits to get the total pixels. 800,000. So yeah, in this question, they do not allow you to use a calculator, so yeah, you're out of luck there. So 800,000 times 5 is 4 million. We got 4 million bits, which is a big one. So now we need to do 4 million divided by 8 times 1024, which is going to, so 4 million divided by 8 times 1, so 8 times 1024 is going to be 8,192. So if we divide the two together, that's going to give us 488.20 kilobytes. So round it off. So that would be the exact answer, but we can round it to 500 kilobytes. So the color depth, so that is what we're indicating. So the correct answer is going to be 500 kilobytes. If the incorrect answer is given, the maximum amount of marks you'll get out of 3 is 2. But we've got the workings nonetheless. So if you get everything right, it's 3 marks, obviously. Okay? And that is that. On to the next one. So we've got an algorithm in figure 0.1 where we're converting binary data entered as a string by the user into a representation of a black and white image. So the plus operator concatenates the strings. Characters in a string are indexed starting at 0. So B data with 2. That will access a third character of the string stored in a variable B data. So the MOD operator will calculate the remainder after the integer division. So there's the MOD. So we need to complete the trace table for the algorithm in figure 0.1 where the variable B data is given the following value from the user. So here is our trace table. And this is what we will need. So, for example, in 0, we're going to have I in 0 is just going to be a divide. Index 1, we're going to have 2 divides. Index 2 is going to be divide and a times. 3 is just going to be a divide. Index 4 is going to be a divide and a times. Index 5 is going to be divide, a times, and a divide. So what we can see here, so the user input, so if B data is 0, then it's going to concatenate with the times, else it's going to concatenate with a divide. And if the MOD is then mod 3 equals to 2, then we're going to output the image. Okay, so that is how that trace table works. On with question 2. Describe how a linear search algorithm works. So the way it works is we start at the beginning of the array and compare each element until the value is being searched for is found, or any array if it's not found. Easy. Another one. State the name of the logic gate represented by the following truth table. So we can see that 0, 0, 0, you can see if there's a 0, the output's going to be a 0. So both inputs are a 1, output being a 1, it's an AND gate. Nice. Nice and simple there. Bosh. Okay, so we've got a partially complete logic circuit as shown in figure 2, detecting if a computer system's been set up correctly. There's 2 keyboard input devices. Keyboard A and keyboard B are either one that can be connected to a computer. If they're both connected, then the computer's system will not work. So output P has a value of 1 if either keyboard A or keyboard B, but not both, are connected to the computer system, and a 0 otherwise. So that's the scenario, and here's the question. So if we were to do L1 is going to be a NOT. L2 is going to be an AND. L3 is also going to be an AND, and then L4 is going to be an OR. So they would be the logic gates that should be placed in those positions indicated by the labels. So L1 is NOT, L2 and L3 are AND, L4 is OR. Next question, question 4. So the algorithm in figure 3 is used to check if the start of an instruction for a particular assembly language is valid. So the string representation of the assembly language instruction is stored in the variable inst str. So characters in the string are index starting at 0. So if we got index 2, that would access the third character of the string stored in a variable. So, looking at this figure, we need to shade one lozenge to show the most appropriate data type of the variable I in the algorithm. So, that will actually be that. So, for 1 mark, out of character, integer, real, or a string, it's actually going to be an integer. Okay, so that's an easy one there. For part 2, we need to state the data type valid in the algorithm point figure 3. So valid, so you can see valid is up here. That's false, that is a boolean. So we would write boolean in here. Part 3. We need to state the final value of the variable valid in the algorithm in figure 3 for the following different starting values. So if we go add is a mnemonic in assembly language, and R0, R1, they're your variables. So the final value is going to be, you would put false. If you go add, then RO, R1, final value is going to be true. Halt, which means end the program, that's going to be true. So, and that is all you need there. Part 4, state what assembly program must be translated into before it can be executed by the computer. It's machine code. Nice and simple. Part 5, we need to state 2 reasons why a programmer who can program both high-level and low-level languages would usually choose to develop a high-level language rather than a low-level. Reason 1, high-level languages are better supported. Reason 2, high-level languages provide built-in subroutines. That's all you need to say to get your full marks. You could say high-level languages allow for the creation of subroutines, they provide data structures, they're easier to debug, and they're easier to understand and read by humans. And high-level languages provide programming structures such as iteration and selection. So these are some of the reasons. Part 6, we need to now develop an algorithm that will use either pseudocode or a flowchart. So it needs to initialize a variable called regValid to false, set a variable called regValid to true if the string contained in the variable reg in the uppercase R is followed by a character representation of a single numeric digit. So examples are, if the value of the reg is R0 or R9, regValid should be true. If it's R6 or RH, false. You might want to use a subroutine isDigit in your answer, and the subroutine isDigit returns true if a character parameter CH is a string representation of a digit and false otherwise. So, you don't have to have a subroutine, but you can have it, which is what they're saying. So, I would have something like regValid. We set that to false. So that's part A. That's 1 mark. Part B, we need to use the Boolean condition that checks the first character is an R. So you could have if reg index 0 is equal to R, and you could have isDigit reg 1. Then we're going to have regValid is equal to true. You would need to do the arrows as part of the AQA pseudocode. So like this. So this is how you would actually do the arrows when we're initializing variables. Next bit is we are going to have endif. So that is a fully correct answer with only 4 lines, which is all you need to get your full marks. You can have others We could have if reg's are. You could have a nested if and else statement, but I wouldn't because it takes more lines. Or you could have of another fully correct answer, but I would keep it to that because it's efficient. We've got what it needs to do. Bosh, done. They will accept minor changes to variable identifiers if the meaning is still clear. So that is a type of answer that I would do. So there's not much to it. Right, number 5. The algorithms in figure 4 and figure 5 have the same purpose. So the operator left shift performs a binary shift to the left by the number indicated. So we got 6 left shift 1. We'll shift the number 6 by 1 place, which has the effect of multiplying the number 6 by 2, giving a result of 12. So this is figure 4 and 5. So you got your results, doing a shift, and then you got your for loop in figure 5. So we need to complete a trace table that will be shown in figure 4 when the initial value is a 4. So in this one, the first one is going to be 16. Okay, the first value is going to result in 16 because the initial number is 4. We're left shifting that by 2, which means multiplying that, which means if we go back up, multiplying that by 1 place, multiplying that by 2, giving us an 8. So multiplying that by 2 to give us 16. And then in the other one, the second result, the last value will also result in a 12. And that will get us 2 marks. If you've got more than one value given for the result, the maximum you'll get is 1 mark. So you would need 16 and 12. That would get you 2, according to the AQA mark scheme for that particular paper. Right, let's press on. We now need to compare the trace table for the algorithm figure 5 when the initial value of the number is 4. So we need to look back on 5. Result is 0. So 4x is 1 to 3. So we're repeating the result, incremented the result plus a number 3 times. So that's what we're doing there. So if we go back down here, what we are going to find is we're going to find x. We're not going to have anything here. So all we need in the result is a 0. In x, we're going to have 1. And the first result is a 4. And then in the second result, as we're adding, we're going to add 4, which is 8. And then index 3, we're going to have 12. So that is how that works. So we're initial number's 4, so we're adding 4. So we start from 0, add 4 once, add 4 twice, add 4 3 times. Do something like that. That's your 4 marks right there. Nice 4 marks right there. No dawdling, no messing about. Bosh, done. Right. Let's get to part 3 of question 5. The algorithms in figure 4 and 5 have the same purpose. State the purpose. The purpose is to multiply the value in the number by 3. Done. They will accept the value of 4 instead of number because 4 has been used in the question. Done. Okay. Now we need to explain why the algorithm shown in figure 4 can be considered more efficient than the one in figure 5. Well, because the algorithm, it's a 1 mark question and they've got a selection. The algorithm in figure 4 will execute in less time. That's 1. Or you could have figure 4 uses fewer variables. Figure 4 uses fewer instructions, so will take up less memory. Or you could have opposite statements for figure 5. Done. That's that one done. Bosh. Right. Number 6. A little bit more involved. So we need to show the steps involved for either the bubble sort algorithm or the merge sort to sort the array in figure 6. So the result is 1, 4, 5, 8. So at the moment, we've got 8, 4, 1, and 5. So we can either do a bubble sort or a merge sort, and we would have to circle the one we want to do. So let's say I want to do a bubble sort. So let's say I want to do a bubble sort. So I could say, we're literally writing down the instructions. So you say 8 and 4 are swapped. 1 and 8 are swapped. So what it's doing is, it's seeing which number is bigger than the other. So is 4 bigger than 8? Nope, they get swapped. 1 and 8, they're going to get swapped. 5 and 8 are also swapped. And then we're going to have 1 and 4 are swapped. So we're swapping the two consecutive numbers if the left number is greater than the right number. And it's going to repeat those passes until no more swaps are made. We could also have done this by diagram, where both lines would be required, but I wouldn't do it for this case. I would just do it like a little list like that. If you decide to do a merge sort, however, so what we would need to do here is we would need to separate the array into arrays containing one element, combining the pairs of arrays and then ordering the numbers together. So in this one, you would need, let's say you've got 8, 4, 1, and 5. We are splitting those up. 8 and 4, 1 and 5. Then we've got 8, 4, 1, 5. So what we need to do is we need to bring them back. So we're going to do 4 and 8 in order. Then we're going to have 1 and 5 in order. And then we're going to have 1. Final answer is going to be 1, 4, 5, 8. And either of those options would get you 4 marks. Bosh. Done. Okay? So that is how I would do it. No messing about, no dawdling. Let's get on with it. Right, next one. Question 7. 4 subroutines are shown in figure 7. So this is quite a big one. So we've got 4 subroutines. So what we need to do is complete a table showing all of the outputs from the subroutine called main3. So we need to have a look at main3. So we got main, and so k is the parameter, and so we're going to do 3 as our parameter. So it's going to output, say 3. 3 greater than 1. If it's even, then it's going to decrease, else it's going to increase. It's going to output the number, whether it's increased or decreased. Then we're going to end the while loop and then end the subroutine. And you see decrease and increase. They're 2 subroutines on their own. Then the is even is another subroutine on its own, checking to see if it's modulus of 2 and it's returning true or false. So that's quite a big one. So the initial output is a 3. So let's say in that, so the first calculated value is going to be a 10. So that's going to increase. So the way we would then need to do that And then let's say the main is 5. Is that greater than 1? Yes. Is it even? Is it even? No, it's not. So we're going to increase that. So 10 division of 2, that's going to result in a 5. So that's going to be a 5. So that one is going to be a 5. And then the next one, we're going to have 16. After that, we're going to have an 8. Then a 4. Then a 2. And then a 1 in this order. So we've calculated the value of 10 at first. And then the next calculated value is going to be a 5. Then 16. And then 8, 4, 2, and 1 in that order. So if you have an incorrect value, that's where they would have stopped marking it. So you get a maximum of 3 marks if you have any additional outputs. So if you have those outputs and no more, you're fine. Okay? Right, part 2. So we need to describe how a developer has used the structured approach to programming in figure 7. So you have 2 options and there's loads. The developers use parameters and they've used return values. So if we go back up on the subroutine, you can see that they've used parameters, they've used return values, they've used local variables, and they've created interfaces to the subroutines. And the problem has been decomposed, and the program has also been modularized. So all of those are essentially answers to number 2, but they only want 2. So I would say developers use parameters and they've used return values. Done. Right, number 8. So we got the subroutine, code to char can be used to convert a character code into corresponding Unicode characters. So 97 is going to return an A, 65 is going to return a capital A. Subroutine chart the code can be used to convert Unicode into corresponding character code. Lowercase a will return 97, uppercase A will return 65. So we need to shade one lozenge to show what the value will be, what value will be returned from the subroutine call code to char 100. So by doing 100, it's actually, so 97 is going to be lowercase a, 98 is going to be B, 99 is going to be C, 100 is going to be D. Done. Right, next one. We need to state the value that will be returned from the subroutine call code to char to code E plus 2. That is going to be a G. So E, if we have a look back up, A is 65, B, capital B is 66, capital C 67, capital D 68, capital E 69. So plus 2, that's going to be a capital G. And it has to be uppercase G. If you put lowercase g, you're not going to get the mark. Has to be uppercase. Okay, so while the subroutine to lower is using either pseudocode or flowchart that takes the upper class character as a parameter and return the corresponding lowercase character. So for subroutine to lower is passed, character capital A as a parameter, subroutine should return the character small a. So you should make use of the subroutine code to chart and chart the code in your answer. You can assume that the parameter is passed to the subroutine in the uppercase. So it's basically saying using either pseudocode or flowcharts. You can do flowcharts if you want, but in this case, I'm going to use pseudocode because it's quicker to go through as well. So all you would need, subroutine to lower, and we're going to have upper as one of our examples. Then we're going to have code. So code is going to be char to code upper. And I'm going to have code plus 32. So we're adding to that. Then we're going to have lower, code to char. Then we're going to pass code into that. Then we're going to do return lower. And then we're going to do end subroutine. So that is one example of a fully correct answer. So we got A, where we've identified to lower, and one parameter, that's 1 mark. Using a char to code with a variable parameter, that's 2. By adding 32 to the result of B, to mark whatever we've done for mark B, that will get you another mark. And then using the result of mark C as the parameter, from the code to char subroutine, that will get you another mark. And then you get another mark just for saying return lower. So do something like that, that's 4 marks. There are some other examples of fully correct answers, like these. So you'll have code, character to code, return the code to character, code plus 32. You could have had that, gotten your 3 marks in one. Or you could have subroutine to lower, upper A, and return code to char to code, upper plus 32. So any of those would have got you 4 marks. Okay? Right, let's move on. Number 9. A developer needs to store data about thousands of songs in a program. She needs to be able to hold information on every song's title, singer, and year of release. And then explain how a developer could use a combination of an array and records to store this information. In your answer, you need to refer to the data types that be used by the developer. So 4 marks, you can say a record could be used to store data in one song. That's 1 mark. And then we need a justification now. Song title could be a string and the singer could be a string. Done. Or you can have an array that could store all the songs, with the song title being a string and the singer can be a string. So, or you can have the year of release could be an integer or a date. If I was doing this, I would say a record could be used to store the date of one song. The song title could be a string, the singer could be a string. And an array could store all of the songs and records. Done. That is 4 marks there. Number 10. Application allows only 2 users to log in. Their username stated in table 1 along with the passwords. Username Gower and Tough with their passwords. So we need an algorithm of either pseudocode or a flowchart that authenticates the user. So the algorithm needs to get the user to enter their name or password, check that the combination of username and password is correct, and output the string access granted. And then get the user to keep re-entering the username until the combination is correct. So there's 2 fully working answers, which is what we could have. So these are 2 working answers that you could have. So we got repeat. We're repeating part C. And then what we're doing in here, username is user input and password is user input. So we are repeating that until the password is equal to username is equal to Gower and password is equal to is equal to this, or the username is tough and the password is equal to this password. And it's going to output access granted if it's the case. In another example, we've got something fairly similar, but this time we've got while not. So we've got while not username is Gower and password is not this, or username is equal to tough and password is equal to that. It's going to ask us to do the username and password as user input until they're both correct. And then it ends the while and we output the final result. So any of those would get you a full 6 marks just by doing the pseudocode. So repeat as the start of the iteration. So saying, right, do this and do this until these both conditions are met. Once they're met, then it outputs access granted. Right, on to the next one. 11. So we need to develop an algorithm using either pseudocode or a flowchart that helps an ice cream seller in a hot country sell how many ice creams they're likely to sell on a particular day. Another anecdote coming at the end, so watch it. So we need to get users to enter whether it's the weekend or a weekday. Get the users to enter the temperature, forecast in degrees Celsius, a number that's between 20 and 45 inclusive, and if a number falls outside this range, should be made to re-enter another number until they enter a valid temperature. So we need to calculate the number of ice creams that are likely to be sold using information. 100 ice creams are likely to be sold at temperatures between 20 and 30 degrees inclusive. 150 if the temperature is going to be 31 to 38 inclusive, and 120 if it's 138 or more. If it's a weekend, we need to double the estimate and then output the estimated number of ice creams likely to be sold. So that is quite a big one. That's quite a big bit of code. So we can have a variable called isWeekend, and we're going to have that as a user input. Temp is going to be equal to user input. And then we need a while loop, so while temp is less than 20 or temp is greater than 45, temp is going to equal user input. And then we end the while. Nice and easy. And then we will need to do the same for the others. And then we are essentially doing the same for the others. So as temp is less than 30, then we need the ices to be less than 100. Less than 100. Then else, if temp is less than 38, then we're going to do ices 150. And then else, we're going to have ices. That's going to be equal to 120. And then we're going to end the if there. And then what we need then is if is weekend is equal to the string yes, then we need to do ices is ices times 2 because we're doubling it. Then we end the end if, and then we output ices. And that is what we got there. So if you're lucky enough to be in the UK and you're waiting to decide, okay, what do I want? Take you about a couple minutes to decide. They'll probably be a bit chilled about it. Well, let's just say if we go to some other country, they might be like, hurry up, I haven't got all day. And don't care if you're 10 years old or not. Trying to decide. Yes, don't go to those places where they're like, hurry up, I haven't got all day. Right. That's enough of the rant. Yeah, should see my rant should see some of my rants, but I'm not going to do any more until the end. Next one, number 12. Last question, you'll be pleased to know. So, number 12, developers written a set of subroutines to control an array of lights. The lights are indexed from 0. They are controlled using the subroutines in table 2, like switch, neighbor, range off. So you've got the array indices. They're shown in the array of lights. So, for example, a string of array of lights is off, on. Then after the subroutine called switch 2, it's going to be off, on. After subroutine call neighbor 0, it's on. Range off is 0 to 3. Array of lights is going to be on, off, on. So, if the array of lights is on, off, on, what will the array of lights become after the following algorithm has been followed? So, in the first one, in the following array, so we're doing switch A plus 1, neighbor A minus 2. So, first one's going to be off, then on, then off, on. So that would be the indexes for the first one. So we got A is 2, we're switching A, so, and then A plus 1, and then we got A minus 2. So if we have a look, so switch is index N is set to off, and N is off is set to on. Okay, that's the first one. Right, let's try this one. If the starting array of lights is off, on, what will the array of lights become if we have this following algorithm? So this is where we need to write the answers. So if we have a look, 0 to 2, 0 is going to be on, 1 is going to be on, and 2 is going to be on. Whilst the rest of them, that's going to be off, but because you've got the range off b divided by 2, 6, and index 6, that's going to be on. That's that one done for the books. Something like that. Answer like that. 3 marks. Bosh. Done. Right. On with the last two. Home stretch. Let's get an home stretch. So if we got to start an array of on, we've got off, on, off, off. We're going array of lights will become after this algorithm is followed. So again, we write our answer in here. So the first one is going to be on, because 0 is set to on, and then 1, which will mean the index is off. Then number 2 is going to be on, and then number 3, that's also going to be on. And then number 4 is going to be off. And then number 5, that's also going to be off. B is 5. And then number 6, that is also going to be on. So that works like a charm. So if you've got something like that, that is going to be 3 marks. Right. Core blimey. End of questions. End is in sight. So for the array as starting lights is on, all ons, and then write an algorithm using exactly 3 subroutine calls means that the final array of lights will be all off. So we have to use each of the subroutines, switch, neighbor, and range off, exactly once in our answer. If you don't do this, you will be able to get some marks, but not all of it. So a couple of ways you could do this. I'm going to show you the one. So you could have range of 0 to 6. 0 to 6, that's 1. And you're going to have neighbour is 0. And then switch being a 6. Done. Or what you could do is you could switch those round. So you got range off is 0 to 6, switch is 6, and neighbour is 0. So if you switch those round and have the range off, you're still going to get your 3 full marks. So that's me gone through an entire past paper that is supposed to last you for 1.5 hours, and I've gone through that in half a time because I'm one of those people who likes to deliver it quickly, concisely, and the best of my ability, and not be like one of those. Yes, God bless one of the students I've had, who basically has a computer science degree who, let's just say, doesn't just fart more than just farts around the subject, but comes up with nonsense analogies on recipes that means absolutely bugger all to most people who are actually interested in computing. But hey, if he finds doing analogies on recipes is the way to go, then hats off. I'm very surprised how people get good A-level results under that guy. But hey, that is the whole of paper 1 of the AQA spec for 2020 GCSE Computer Science. So you have that comprehensive walkthrough. So practice makes perfect, so grab some past papers, give it a go. If you found this video helpful, don't forget to hit that like button and share it with your fellow coders and computer science students. Subscribe for more content like this, and as always, happy coding. So thanks for joining us today on Learn Computing with Daniel Bullen. Until next time, keep coding, keep exploring, keep practicing, and keep being awesome. Bye for now.